Welcome, everyone. Thank you for joining us for episode 39 in the Gleeble webinar series. My name is Dan Quigley, and it's my pleasure to welcome you to our little online community of researchers. We know how valuable your time is. There's a lot of webinars, conferences, training sessions, meetings, and YouTube videos, and a lot of other things competing for your time. So we appreciate you spending time with us, and we have a very interesting presentation today focusing on heat treatment and continuous annealing line simulations. We think you'll enjoy it. Today's presenter is Jarek Opara. He's Chief Specialist in the Research Group at the Institute for Ferrous Metallurgy, also known as IFM. The title of today's presentation is Heat Treatment Simulations, Reproducing a Continuous Annealing Line of Dual Phase Strips Using the Gleeble 3800 System. The presentation will show an investigation of the continuous annealing galvanizing cycles of cold rolled sheets of a selected dual phase steel, the characterization of the effect of heat treatment parameters on the mechanical properties and structure will be presented. Simulations of heat treatment in the Gleeble 3800 will be demonstrated with the application of different parameters which fall into two categories. The first category embraces annealing over a two-phase temperature range followed by water cooling, and the second is the same but succeeded by tempering. Furthermore, two kinds of samples will be depicted, one with a standard 2-inch specimen and the second with a modified shape. As always, we will endeavor to keep this webinar to 1 hour or less. We should have some time at the end of the presentation for a live Q&A. If you have questions, please submit them using the chat feature right here in the webinar software, and we'll take a handful of those questions and present them to Jarek at the end of his presentation. Video of this presentation will be available online soon, and certificates will also be emailed to you if you're listening to this live. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com, and then click on the resources link in the top navigation bar, and then on webinars, and there you'll see a long list of past webinars, and you can sign up for future webinars. The next webinar will be held on Thursday, July 29th. And that link is active, so you can sign up for that when you get a moment. But without further delay, it's my pleasure to hand this over to Jarek from IFM. And I think, Jarek, we can hear you, so take it away.
Okay. Good morning, good afternoon. Welcome everyone to the webinar. Before beginning, I would like to thank Dan and our crew of DSI for inviting me to give this talk. As Dan said, I am Chief Specialist at the Łukasiewicz Research Network, Institute for Ferrous Metallurgy. My research interest is phase transformations and investigation on it using Gleeble simulator and dilatometry. I also deal with modeling these phenomena using the classical mean field approach, like JMAG model, as well as the serial automata technique to model microstructure evolution at mesoscale. The agenda of my talk today will go through presentation of the company Łukasiewicz Research Network, Institute for Ferrous Metallurgy. Second, I want to give an introduction for the motivation of the continuous strip annealing physical simulation. In the third point, I will shortly describe the experimental material and methodology. Subsequently, I will show the selected results of the continuous annealing simulations with the quantitative characterization of the phase transformations. In the next point, I will demonstrate examples of the continuous strip annealing numerical simulations. And finally, I will summarize the presentation. The Łukasiewicz Research Network was established on 1st April 2019, including 33 institutes. We form a group of 8,000 employees, together with a group of 4,500 scientists. We have great human resource and equipment potential, capable of creating comprehensive strategic programs in 4 stated development directions: health, smart mobility, sustainable economy and energy, and digital transformation. The patron of the Polish Research Network is Ignacy Łukasiewicz, born in 1822 in Zaduszniki. He was a Polish pharmacist, entrepreneur, community activist, patriot, philanthropist, and the inventor of the kerosene lamp. The Łukasiewicz Institute for Ferrous Metallurgy is located in Poland, Europe, for more specifically in Gliwice City, Silesia district. We are providing scientific research and consulting services for the industry and public institutions. The institute employs 108 people, including 4 with professor's title, 7 with habilitation title, and 25 PhDs. The Łukasiewicz Research Network Institute for Ferrous Metallurgy is an institute dealing with the development of new technologies through research and in cooperation with industry. The institute's activities are focused on issues related with materials engineering, enabling comprehensive research and pilot studies mainly for industry. The Łukasiewicz Institute for Ferrous Metallurgy consists of 6 research groups divided according to their specification as follows: analytical chemistry, material research for power engineering, investigation of properties and structure of materials, primary processes, manufacturing technology and application of products, and my research group, processes simulation. Current research directions of the research group, processes simulation, are as follows: physical and numerical processes simulation, continuous casting, thermomechanical processing, continuous annealing of finished sheets, heat treatment, material models, rheological, microstructure evolution during thermomechanical processing, phase transformations, development of processes parameters, rolling of flat and long products, forging, continuous annealing, heat treatment, designing the chemical composition and parameters of rolling technology for modern magnetic steels and steel for the power industry. Research on the degradation processes of the structure under the condition of the synergistic effect of thermomechanical fatigue and creep at ultra-high temperature. The foundation of the Laboratory of Process Simulations, right now called Research Group Processes Simulation, was begun with the purchase of the Gleeble 3800 simulator in 1999. Using the Gleeble system, we are conducting physical simulations of the following processes: continuous casting of steels, hot rolling, continuous annealing of car body sheets, heat treatment, technological operations in the field of powder metallurgy, extrusion, change occurring in the heat-affected zone of weld, resistant welding, joining materials with diffusion, thixoforming. We also determine material characteristics using Gleeble in the field of thermomechanical processing, continuous casting, creep and thermal mechanical fatigue, welding, phase transformations. In our laboratory, we have a quenching dilatometer DIL 805 AD with the ability to deform the spaceman by compression produced by Baer in the early 90s. And also we have the newer version of it, delivered by TAA Instruments, that can also stretch the sample in tension mode. It says DIL 805 ADT. Generally, the dilatometer allows for the investigation of phase transformations of alternate non-deformed and deformed in the course of full samples compressing and round and flat sample stretching, investigation of sheet metal. Apart from the linear variable differential transformer system, the dilatometer is equipped with optical contactless system for measuring diameter changes in sample during a programmed thermal cycle. This system allows for independent temperature measurements in 3 points of the sample. The dilatometer's control system allows for the conduction of thermal and thermomechanical cycles as well as short-term creep tests. Our research group is equipped with a salt spray test chamber HKT 500 with a capacity of 500 liters. The salt spray chamber is used to set the anti-corrosion quality of all the material surfaces of painting, coating, electroplating in the condition of salt spray environment in accordance with ASTM, DIN, ISO, IEC, and other international standards test methods. We have designed and constructed a few devices that allows performing dedicated investigations like device for accelerated controlled cooling of long products such as rails, HDG simulator to hot deep galvanizing of strip samples. In our laboratory, we are able to conduct thermodynamic calculations using Thermocalc, Dictra, Prisma, JMAT Pro. We also commercial software such as the Procast for the numerical simulation of the continuous casting process or the Forge program for the numerical simulation of forging. We developed our own computer programs which allows modeling of CCC diagrams using JMAC or Kikaly's approach and a separate modeler for quantitative dilatometric analysis, giving an evaluation of the phase transformation's kinetics. Numerical simulation of phase transformation is still using digital material representation concepts that give direct observation of microstructural evolution and carbon segregation using a cellular automaton model. In recent years, the automotive industry has been searching for new material solutions to design lightweight and crash-safe vehicles. This is due to the continuous evolution of the customer's requirements and also in line with existing safety and environmental standards associated with low carbon dioxide emission. The most demanding expectations are the reduction of fuel consumption to low production costs and smart design. The other performance requirements of an automobile body structure include structural static stiffness, crashworthiness, durability, harshness, noise, and vibration damping. In order to meet these demands, innovative advanced high-strength steels are under development. The characteristic feature of these multi-phase steels is an outstanding combination of high-strength properties with good ductility, which is a prerequisite for high energy absorption during a crash. One of the most important categories of advanced high-strength steels are dual-phase steels. Thanks to the combination of high strength, good formability, and low cost, as well as high work hardening, which implies a high energy absorbing ability or crashworthiness, DP steels are mainly used by the automotive industry, primarily for safety parts in car bodies, exemplary criteria bumpers, B-pillars, side impact beams. Typically, the structure of DP steels is obtained by annealing at an intercritical range austenite plus ferrite, followed by controlled cooling at rates allowing the transformation of austenite into fresh ferrite and subsequently into martensite. Although this category of steels has been known for over 30 years, now grades with improved properties are still under development. Another way to produce DP steels is continuous annealing to the full austenite region and next complex cooling. Both of these processes are fast and takes about 300 to 500 seconds. Although a general knowledge of the relations between microstructure and mechanical properties of DP steels is well known, specifically the effect of martensite volume fraction. Many functional properties are dependent on discrete and not typically quantified features of their microstructure. One of them is the carbon profiles formation during complex cooling in the austenite grains, which strongly influences the formation of hard constituents during cooling. Controlling the carbon redistribution and carbon profiles creation in austenite grains is one of the crucial ways of developing the properties of DP steels. Generally, during strip continuous annealing, we can distinguish the following stages: heating, during which recovery and recrystallization of ferrite occur, as well as cementite dissolution; soaking with ferrite plus perlite to austenite phase transformation; slow cooling, during which austenite to ferrite phase transformation occurs; galvanizing with austenite to bainite phase transformation; fast cooling, during which austenite to martensite phase transformation occurs. Presently, the measurements undertaken for the improvement of the physical properties mainly concern the optimization of continuous annealing parameters in industrial lines for the production of sheets. This target can be achieved with the aid of physical simulations as well as numerical modeling of the manufacturing process of these sheets, aimed at the analysis of the process parameters on the obtained structure and the mechanical properties. To meet these challenges, the WetSheets project was established in 2011, which was financed by the European Commission Research Programme of the Research Fund for Coal and Steel. Some partial results of this project will be nextly presented. The project was aimed at the development of a physically based model for continuous annealing galvanizing process capable of identifying the quantitative effect of chemical composition and thermal cycle on the microstructure of DP sheets. The research material was a cold rolled sheet of DP steel. The rolling was conducted in several passes to reduce the thickness of the hot rolled strip from 3 mm down to 1 mm. The chemical composition of the investigated sheet is shown in table. The selected steel was characterized by its lean chemical composition, specifically low silicon content, and was intended to tackle common problems encountered during hot dip galvanizing of sheets. Experimental methodology consists of strip continuous annealing simulation using Gleeble 3800 system, density tests and hardness measurements, microstructure characterization using light optical microscopy, high-resolution scanning electron microscopy equipped with EBSD, and scanning transmission microscope. The samples machined from the cold rolled sheet for examinations were subjected to the heat treatment pre-producing and continuous annealing and galvanizing process using a Gleeble 3800 simulator with the standard mobile conversion unit. The geometry of the samples applied for the simulations is presented in the figures. This shape allows the performance of the tensile strength to be directly measured after simulations were completed. The effect of the maximum temperature, soaking time at this temperature, and temperature time is considered to be fundamental for the continuous annealing process, and these are varied in the performed experiments. All simulation parameters are presented in the figures. Two types of schedules have been performed. Schedule A, soaking in the two-phase temperature range, followed by water cooling, with the aim of analyzing the effect of maximum temperature and soaking time on the structure and mechanical properties. Schedule B, the same as A, but followed by tempering at different temperatures and holding times. On this slide, we can observe FEC-SEM structures of the samples with increasing soaking time ranging from 0 to 60 seconds at 780 centigrades and at 810 centigrades. Quantitative analysis of structural constituent components show that an increase in the soaking time from 0 to 60 seconds at both temperatures leads to an increase in the martensite plus bainite area fraction from 17.6% to 25%, and from 24.8% to 33.8% respectively. It should be noted that the samples soaked at 800 centigrades with the same values of the soaking parameters, giving a higher area fraction of hard constituents compared to the samples after soaking at 780 centigrades. The increase in the area fraction of martensite plus bainite with increased soaking time is also associated with a slight decrease in the ferrite grain size. The mechanical properties of the samples after the performed test according to the Schedule A are given in table and in chart below. The increase in soaking time at 780 centigrades results in the ultimate tensile strength increase from 586 megapascals to 626 megapascals, whilst proof stress maintains at approximately the same level of around 300 megapascals. Conversely, at the soaking temperature of 810 centigrades, both proof stress and ultimate tensile strength increase as the soaking time increases. The yield ratio in the range of 0.49 to 0.58. This is an indication of a good work hardening of the samples. Elongation to fracture doesn't depend substantially on the soaking time and varies in the range of 15 to 19%. On this slide, we see the exact same structures of the samples after tempering at 230, 380, and 460 centigrades for 240 seconds, following schedule B. The structure of all these samples are composed of ferrite, tempered bainite, and martensite. It can be observed that single carbides precipitate in the martensite plus bainite islands. Initially, they are characterized by fine needle-like morphology. The process of carbide spheroidization in the martensite areas is intensified with an increase in the tempering temperature. The results of mechanical properties measurement following the simulations of tempering are given in table and charts below. Tempering at 230 centigrades doesn't significantly affect both the proof stress and elongation to fracture. Ultimate tensile strength decreases with increasing time and following tempering for 240 seconds at 230 centigrades is 581 megapascals. A further increase of tempering temperature to 380 centigrades and 460 centigrades transfers proof stress to yield strength with an apparent yield point. Yield strength increases, whereas ultimate tensile strength decreases, with an increase in the tempering temperature. Tempering at highest temperatures leads to the decrease in the yield ratio, whereas elongation to fracture is similar to the value measured following quenching. The samples soaked at 810 centigrades and followed by subsequent tempering at all variants of the parameters are characterized by higher values of mechanical properties when compared to the same tempering parameters for samples after soaking at 780 centigrades. A slight lowering of the ultimate tensile strength and increase in the elongation to fracture is observed following tempering at 230 centigrades. Tempering at higher temperatures, 380 centigrades and 460 degrees, leads to the increase in yield strength and simultaneously the decrease of ultimate tensile strength. Moreover, in all cases, an increase in the tempering time leads to a small increase of yield strength and lowering the ultimate tensile strength. One of the objectives of the VetPrits project was modeling of the continuous strip annealing using digital material representation concept and cellular automata phase transformations model. The whole modeling approach consists of several submodels. First model is for cold rolling, second for heating, next for soaking intercritical annealing, and the last for cooling, considering three austenite phase transformations into ferrite, bainite, and martensite. Based on the volume fractions and kinetics of structural constituents formed during cooling, the mechanical properties model allows to forecast the mechanical properties, which are next compared with experimental data. Here is one of the examples of continuous strip annealing numerical simulations at the intercritical region. As one can see, a very good convergence of simulation results with experimental data was obtained. On this slide, we can observe CA modeling approach that allows the 2D visualization of the changes occurring in the microstructure during the annealing galvanizing process. Specifically, it allows tracking the distribution of carbon in the microstructure at subsequent technological stages, which is essential for the distribution of microstructural constituents in the final microstructure, and thus on mechanical and use properties. That was one of the crucial aspects to build this model and finish the project VetPrits. Summarizing. The structure and mechanical properties of the investigated DP steel is mostly influenced by temperature and time of intercritical soaking. An increase in the soaking time and temperature leads to an increase in the martensite plus bainite area fraction. This results in an increase of ultimate tensile strength and proof stress for the case which is soaked at 810 centigrades. An increase of soaking time to 780 centigrades doesn't result in an explicit increase of proof stress because the ferrite grain size is comparable among the samples. During heat treatment, globular carbides of cementite enriched in manganese and chromium present in the cold rolled sample transform into M73-1s. An increase in the tempering temperature from 230 centigrades and above 380 centigrades results in the appearance of a yield strength in the stress strain curve instead of a proof stress, and decrease of ultimate tensile strength. The change of proof stress into yield strength is the effect of the aging of the ferrite. Tempering at the temperatures above 230 centigrades leads to the deterioration of the work hardening characteristics, resulting in an increase in the yield ratio. Presumably, this is a result of an increase in the number of precipitated cementite carbides in the hard constituents with increasing tempering temperatures. General findings of the work are as follows. By varying the thermal cycle parameters, heating and cooling rates, and/or soaking temperatures, it is possible to change drastically the final microstructures in terms of phase fractions and their morphologies. The investigation provided the qualitative and quantitative information concerning the mechanism of phase transformations, accounting for the specific features of continuous annealing process. The obtained results were used to develop cellular automata model of continuous annealing process. The cellular automata discrete model can be used in advanced researches aimed at the optimization of the microstructure of DP steels. Specifically, it can be used to affect the carbon distribution in the microstructure through designing the thermal cycle. Since this model is based on the theoretical description of metallurgical changes occurring in the microstructure, it is very useful in analyzing the contribution of different mechanisms to microstructural development in these steels. Thank you for your attention.
Thank you, Jarek. It was a great presentation. Appreciate you spending the time to prepare it and to share it with us, and for presenting live. I know that's always a challenge, especially when we have around the world different internet connections. Mine right here is not great, so if I cut out a little bit, I do apologize. We do have a couple of questions. Couple questions from Dr. Kumar. So actually, if you want to go back to maybe slide 26 or 27.
Okay.
The question was, what was the cooling rate followed by the first heating and after tempering? So maybe you can talk about the cooling rates and heating rates during that process here. It looks like it's listed there, but was it just a free cool?
Okay, cooling rate, it was, I think, about 80 centigrades per second, maybe 100.
Okay, and that goes into the next question is, what is the maximum cooling rate possible in continuous annealing line? And did you use that same cooling rate following the Gleeble simulation? So were you able to use that in the Gleeble simulation as well?
Yes, in the Gleeble, there in the standard unit, there are a problem to let's say control the water quenching. So let's say we obtain about 110 centigrades per second cooling rate. That was, let's say.
Yeah, and are you able to tell us what the maximum cooling rate of the actual line was?
Sorry, I don't.
The line that you were simulating, the production line. What
Okay.
were the maximum cooling rates there?
Okay, I don't have this data right now in the.
Okay.
It was a few years ago, so I don't remember. Sorry.
Sure, no problem. So we have a question here. It says, "Can you?" I think this was near in your question came up during your summary slide, so maybe near the end. But it said, "Can you expect M7C3 carbide in a steel having only 0.35% chromium?"
Okay. Yes, I didn't show the research using transmission electron microscopies, so we have detected these carbides. And could you repeat maybe?
Yeah, it said, "Can you expect?" And I apologize, that the M7C3 carbide in a steel that has only 0.35% chromium.
Okay. Let's say I don't. I'm not sure.
Okay, fair enough. Fair enough. So a question here that we have about, just how you use the Gleeble. So before running a new material on a line, how do you have any sense for how many simulations you would perform before running a new material on that line?
Okay. Let's say we a lot of time we spent on investigation using dilatometry because the samples are smaller and cheaper, and when we figure out let's say the optimal range of coolings, then we produce the samples for Gleeble, and then we could check the mechanical properties, because let's say testing a lot of samples, let's say without any when we are not sure how it will be works. So when we're planning the experiments, we do some experiments on dilatometry. Let's say we investigate the sample with few CCT diagrams. We prepare the CCT diagrams, and when we have the ranges, we could test it on some other thermal cycles on the Gleeble.
Okay. A question here said, let's see, "In your opinion, what is the most effective alloying element to raise strain hardening exponent responsible for improved uniform elongation?" Yes, is there a single alloying element that you can call out?
Yes, I think I'm not.
We don't want to put you on the spot.
Right now, I can't explain this. Answer this question.
Oh, all right. A question here said, "What is the minimum size for a dilatometry experiment?" So which
we use
anyway.
We use samples with the minimum size about 7 millimeters, but there are, let's say, thick with the length of sample is 7 millimeters, and the radius is 4 millimeters.
Okay,
and
so you're doing
flat
that on
samples
a round.
And sheet samples are 1 millimeter thick, and let's say about 4 millimeters width and 7 to 10 millimeters length.
Okay, I apologize. I don't recall. How are you measuring that? Are you measuring that with a optical measurement device or an extensometer?
but samples on dilatometry.
Correct. Are you using? We have the LED optical dilatometer. There's also the clip-on extensometer. Are you using the contact extensometer?
Yes, we use contact.
All right. And here's a question that may take maybe a topic of a whole webinar, but it says, how do you translate JMAK to CCT construction?
We have developed Johnson-Avrami-Kolmogorov equation in a numerical model, and we can simulate each thermal cycle with this model, and it is developed for each phase transformation of austenite, ferrite, perlite, and bainite and martensite. So we can obtain the CCT diagram using these simulations for all, let's say, for all experimental cooling cores.
Great, thank you. So we actually are just about out of questions here. So if you are out there and you do have questions for Jarek or his team, if you'd like to connect with him directly, please feel free to reach out to me or anyone at DSI, and we can connect you. Jarek, I believe you'll be available for questions and connect with people directly. So we're happy to make that introduction. If you have any technical questions about the operation of your Gleeble, please contact our service team. I mention this every week, but we do have a new service portal that includes a useful knowledge base and a very convenient service ticketing system. And that is useful. It's the best way to contact our team because hopefully our guys will be traveling again soon, so they may be on airplanes, and if you're emailing a service engineer directly, they may not be available. So please do use that ticketing system that's available right on our website. If you go onto that resources tab in the top navigation bar, and then click on the customer support portal, you get to sign up if you're a user, but then there is a nice knowledge base there and access to our service engineers so that they're there to help. If you have any questions about how Gleeble can support your research, please email our team, email me or anyone on our team, and we're happy to connect you with an application expert, either in your region or in your area of study, and they're happy to help. I do want to thank everyone for joining us. Jarek, I want to thank you again for the great presentation. I know it's a lot of time and work to present, so we do appreciate that.
Thank you very much.
All right, everyone, please do stay safe and healthy, and hopefully we'll be able to see all of you at a conference in person soon. So until then, be well, and we'll talk soon. Let us know if we can help. Take care.
Take care.